This presentation is about World Water Online, a project supported by the Center for Research in Water Resources at the University of Texas at Austin, Esri, a leading software provider of GIS technology, and Kisters, a water data management group focused on time series solutions. Much of what you will see today is in the pilot stage, however some elements will be released in the upcoming year. There are 4 common problems with respect to water that we are always trying to solve. Sometimes we are faced with too much water in the form of floods, sometimes we experience drought and don't have enough water, and sometimes, even when we have enough water, it is not provided at an acceptable water quality. As water managers and engineers, we must find solutions to each of these problems while still maintaining ecological integrity and supporting biological habitats. Water resource information has value in many kinds of applications, from helping to meet basic survival needs to supporting urban industrial society. World Water Online meets a long-term vision for collecting and sharing water resource information so that anyone with internet access can find out about water conditions in their local area. This is accomplished through a combination of commercial and open source products and services designed for free and open public access. The goal of World Water Online is to empower people through the web and connect them to water data, maps, and models everywhere at many different scales of application, from global to local. One of the services being developed is a global hydro-based map at multiple scales. At the global level, one can see the biggest rivers in the world, symbolized by mean annual stream flow. As we zoom into the country scale, we begin to see more rivers appear, again symbolized by stream flow. This type of base map can help give hydrologic context to much of the work we are trying to accomplish. It demonstrates how hydrologic features relate to our surroundings, and more importantly, how they affect our daily lives. Another service being developed is the Global Watershed Delineation Service, where a user can zoom in and click on any point along a river, and within a matter of seconds, delineate the upstream watershed from that point. In this example, we can see the watershed related to the AIP-5 dam in Brazil. Let's take a look at how this would work. Here we see a map application with a global hydro base map overlaid on top of it. We can zoom in to the AIP-5 dam area, and then click on a point just upstream of the dam to delineate the watershed. This service is being done by a geoprocessing service that is being hosted in the cloud. Within a matter of seconds, it will return the watershed upstream of the dam itself. There we go. If we zoom out, we can see the entire Parana River Basin. We have just seen some examples of services that help provide hydrologic context at many scales of application. Now, how can we integrate these services with data available all over the world? Here are some examples. GRACE, which stands for the Gravity Anomaly and Climate Experiment, is a pair of satellites which has been operating since 2002. These satellites orbit the Earth at 500 kilometers and maintain a distance of 220 kilometers apart. As the satellites pass over different parts of the world, they measure the gravitational force. Because water is so heavy, GRACE data can be used to derive changes in water volume over time at any point on Earth. This can be used to study how much water is gained or lost over an area over a period of time. Similarly, NASA has developed a global land data assimilation system that provides many atmospheric and hydrologic variables, such as precipitation, temperature, evaporation, etc. Here we can see how the watershed delineation services can be combined with other global data services. In conjunction, these services can aggregate or summarize myriad water information over a region. In this example, we can see average monthly precipitation for the Congo River Basin in Africa. However, this service could be extended to interact with GRACE data as well, as discussed in the previous slide. Here's another example of how one could leverage the watershed delineation services here in Brazil. Conducting a water balance for a watershed is often an important exercise as it helps us understand how the system responds to different inputs, in this case precipitation. Here we can see the Parana River Basin, the average monthly precipitation, and the water storage, derived from GRACE, in cubic kilometers. This simple analysis demonstrates how the basin responds to the precipitation. As it rains, the basin gains water and stores it in the system. By keeping the units consistent, we can see how the overall storage in the basin relates to the capacity of reservoirs and dams in the watershed. During a drought, this exercise could be extremely helpful for assessing the available water resources in the area. Because we are working with global data services, we can perform these operations anywhere on Earth and include groundwater, soil moisture, etc. So what's missing here? Stream flow. As part of the World Water Online effort, the University of Texas and others are building large-scale streamflow models that route water through river networks. In this example, overland and subsurface flow from the land data assimilation system are being routed through the state of Texas to the Texas Gulf Coast. Thinking back to the water balance application, one can see how streamflow information can close the loop on the water balance. What comes into the system must come out. It is the goal to utilize the river networks from the delineation service and land data assimilation system outputs to perform water balance calculations all over the Earth. Up until now, we have focused on water data coming from global sources of information, such as satellites and models. However, streamflow and other phenomena within rivers are measured locally and managed by many agencies within the country. So how can we share this type of information within a global system? Water observations data is collected in many different ways using many different types of sensors and collection devices. Every country collects this information and manages it at the local level. It is possible that several agencies within a country are responsible for collecting the same data, however the method in which they manage, store, and distribute that information could be inconsistent, thus limiting their utility. We as a global community are lacking a global water information system for distributing these types of data in a consistent manner. WaterML was developed by QUASI, the Consortium of Universities for the Advancement of Hydrologic Science, Inc., as a language for communicating water observations data over the Internet. Over the last couple of years, WaterML 2 was developed as a profile of the Open Geospatial Consortium's Observation and Measurement Standard. Earlier this year, WaterML 2 officially became the international standard for water data transmission across the web. WaterML data services exist in many countries around the world. The United States Geological Survey in the U.S. published data for over 12,000 gauge locations in WaterML. Similarly, as part of a volunteer effort, the Dominican Republic, in conjunction with Brigham Young University, have created WaterML data services for streamflow and precipitation gauges across the country using open source software created by QUASI. The question is, can we do this at a global scale and create a community map such as this by working with the World Meteorological Organization, the Global Runoff Data Center, and countries all over the world? So how can this be done? How can we manage and distribute data in a federated way? Within World Water Online, there are three categories of data services: catalog services, metadata services, and data services. Catalog services are used to discover who is providing data and what they are providing. In this case, countries within World Water Online would provide catalogs of metadata managed by the different in-country agencies. This could be implemented as a CSW. Each agency would provide a metadata service to the catalog, which stores a collection of time series available as WaterML. This collection would describe the time series by location, variable measured, start and end date, as well as other metadata descriptors. The metadata service could be implemented as a WFS and used to map the locations of the time series. Finally, time series within the metadata service would provide a direct binding to the underlying WaterML data service in order to provide access to that data. In this way, we can provide a systematic and structured approach to publishing water observations data while conforming to open standards. Here is the current architecture for World Water Online within GEOS. A user can search the GEOS registry for World Water Online and access the World Water Online portal or map viewer. If you go to the map viewer, you will see a map containing rendered web feature services representing the locations of monitoring stations. A user can zoom in and select the monitoring station to see a pop-up with metadata and possibly other content as well, such as a graph. If the metadata provides a WaterML URI, the user can click on the link to send a request to the data server, returning WaterML data. In the current architecture, the University of Texas is hosting the metadata services, while the data services are coming from different hosts. Each of these hosts are publishing WaterML data through both proven and industry open technologies. Let's quickly take a look at how a user can search for World Water Online services within GEOS. A user can simply type in WWO within the GeoPortal and quickly pull up all the metadata services registered within the GEOS registry. A user can access these directly or access the World Water Online portal. For this demonstration, let's take a look at the World Water Online map viewer instead. Here, we see a map of World Water Online stream gauges hosted by different data providers. We can zoom into Texas and see a subset of the USGS stream gauges. These gauges are publishing near real-time data, so when a user clicks on the gauge, the user will see the latest value recorded along with some other metadata and a graph. If a user desires, the user can activate the watershed delineation service as well. The eventual goal is to delineate a watershed and select out all the stream gauges within that watershed and download the data directly via the WaterML data services. There are many applications for World Water Online, as water is a vital resource for all forms of life. There are currently thousands of humanitarian efforts all over the world, led by many organizations such as Engineers Without Borders and Rotary International. World Water Online can support these efforts as well by creating a network of humanitarian projects from which people can connect to one another and learn from each other's successes and failures. Water projects in the developing world require copious amounts of information to successfully and sustainably engineer a system. Unfortunately, it is often difficult to acquire much of this information, as data is either not openly shared, not advertised well, or difficult to work with. World Water Online can help meet some of these data needs by providing engineers and volunteers on the ground with information about their immediate environment. World Water Online can help people leverage geospatial and temporal information to design sustainable homes, communities, and societies with respect to their dependence on water. Today, the internet is being used to connect people through Facebook, YouTube, Twitter, etc. We can achieve the same goals in hydrology if we work together. Thank you.